Hello, welcome to Cloud Channel. In this module, we will talk about Amazon Redshift data warehouse, and we will discuss about a Redshift system and architecture overview, data warehouse system architecture, performance, columnar storage, workload management, and using Amazon Redshift with other services, how to migrate data from S3 to Redshift, and how to move data from remote servers to Redshift. Let's start. What is Amazon Redshift? Amazon Redshift is a fully managed petabyte-scale cloud-based data warehouse product designed for large-scale dataset storage and analysis. It is also used to perform large-scale database migrations. An Amazon Redshift data warehouse is an enterprise-class relational database query and management system. Amazon Redshift supports client connections with many types of applications, including business intelligence, reporting, data, and analytics tools. When we execute analytic queries, we are retrieving, comparing, and evaluating large amounts of data in multiple stage operations to produce a final result. Amazon Redshift achieves efficient storage and optimum query performance through a combination of massively parallel processing, columnar data storage, and very efficient targeted data compression and coding schemes. Let's talk about data warehouse system architecture. We can see in the diagram, we can see that client applications, connections, clusters, leader node, compute nodes, node slices, internal network, databases. So let's talk about each in detail. So what are the client applications? Amazon Redshift integrates with various data loading and ETL tools and business intelligence, reporting, data mining, and analytics tools. Amazon Redshift is based on industry standard PostgreSQL, so most existing SQL client applications will work with only minimal changes. Let's talk about connections. Amazon Redshift communicates with client applications by using industry standard JDBC and ODBC drivers for PostgreSQL. So we can always download these JDBC and ODBC drivers to communicate with client applications and Redshift. What are the clusters? The core infrastructure component of an Amazon Redshift data warehouse is a cluster. A cluster is composed of one or more compute nodes. If a cluster is provisioned with two or more compute nodes, an additional leader node coordinates the compute nodes and handles external communication. Our client application interacts directly only with the leader node. The compute nodes are transparent to external applications. What is leader node? The leader node manages communications with client programs and all communication with compute nodes. It passes and develops execution plans to carry out database operations, in particular the series of steps necessary to obtain results for complex queries. Based on the execution plan, the leader node compiles code, distributes the compiled code to the compute nodes, and assign a portion of the data to each compute node. The leader node distributes SQL statements to the compute nodes only when a query references tables that are stored on the compute nodes. All other queries run exclusively on the leader node. Amazon Redshift is designed to implement certain SQL functions only on the leader node. A query that uses any of these functions will return an error if it references tables that reside on the compute node. What are the compute nodes? The leader node compiles code for individual elements of the execution plan and assigns the code to individual compute nodes. The compute nodes execute the compiled code and send intermediate results back to the leader node for final aggregation. Each compute node has its own dedicated CPU, memory, and attached disk storage, which are determined by node type. As our workload grows, we can increase the compute capacity and storage capacity of a cluster by increasing the number of nodes, upgrading the node type, or both. What is node slice? A compute node is partitioned into slices. Each slice is allocated a portion of the node's memory and disk space where it processes a portion of the workload assigned to the node. The leader node manages distributing data to the slices and apportions the workload for any queries or other database operations to the slices. The slices then work in parallel to complete the operation. The number of slices per node is determined by the node size of the cluster. When we create a table, we can optionally specify one column as the distribution key. When the table is loaded with data, the rows are distributed to the node slices according to the distribution key that is defined for a table. Choosing a good distribution key enables Amazon Redshift to use parallel processing to load data and execute queries efficiently. So we do this same thing in Azure Synapse. When we are creating table in Azure Synapse, we choose the distribution keys, either as distribution. If it is a large and fact table, we choose as distribution. If it is a staging table, we choose round robin. If it is a minimum, like under 250 GB, then we choose replicated distribution. In the same way here, we have to choose a right distribution to use parallel processing and load data and execute queries efficiently in Amazon Redshift. Let's talk about what is an internal network. Amazon Redshift takes advantage of high bandwidth connections, close proximity, and custom communication protocols to provide private, very high-speed network communication between the leader node and compute nodes. The compute nodes run on a separate, isolated network that client applications never access directly. Let's talk about databases. A cluster contains one or more databases. User data is stored on the compute nodes. Our SQL client communicates with the leader node, which in turn coordinates query execution with the compute nodes. Amazon Redshift is a relational database management system, so it is compatible with other RDMS applications. Although it provides the same functionality as a typical RDMS, including online transaction processing functions such as inserting and deleting data, Amazon Redshift is optimized for high performance analysis and reporting of very large datasets. Amazon Redshift is based on PostgreSQL. Amazon Redshift and PostgreSQL have a number of very important differences that we need to take into account as we design and develop our data warehouse applications. Let's talk about performance. Amazon Redshift achieves extremely fast query execution by employing the performance features. Massively parallel processing, columnar data storage, data compression, query optimizer, result caching, compiled code. Let's talk about each feature in detail. Let's talk about massively parallel processing. Massively parallel processing enables fast execution of the most complex queries operating on large amounts of data. Multiple compute nodes handle all query processing leading up to final result aggregation, with each core of each node executing the same compiled query segments on portions of the entire data. Amazon Redshift distributes the rows of a table to the compute node so that the data can be processed in parallel. By selecting an appropriate distribution key for each table, we can optimize the distribution of data to balance the workload and minimize movement of data from node to node. So when we talk about choose right distribution key, so we do that same. We choose a right distribution in Azure Synapse to achieve this performance, good performance. So in the same way, we have to choose a right distribution key in Amazon Redshift. And loading data from flat files takes advantage of parallel processing by spreading the workload across multiple nodes while simultaneously reading from multiple files. Let's talk about data compression. Data compression reduces storage requirements, thereby reducing disk, which improves query performance. I think we will discuss about columnar data storage next. So here we discuss about data compression, query optimizer, result caching, compiled code, and massively parallel processing. We already discussed about massively parallel processing. So we are talking about data compression now. So when we execute a query, the compressed data is read into memory, then uncompressed during query execution. Loading less data into memory enables Amazon Redshift to allocate more memory to analyzing the data. Because columnar storage stores similar data sequentially, Amazon Redshift is able to apply adaptive compression encoding specifically tied to columnar data types. Let's talk about Query Optimizer. The Amazon Redshift Query Execution Engine incorporates a query optimizer that is MPP aware and also takes advantage of the columnar-oriented data storage. So before we go to next features, I want to talk about columnar storage a little bit. Columnar storage for database tables drastically reduces the overall disk input requirements and is an important factor in optimizing analytic query performance. Storing database table information in a columnar fashion reduces the number of disk input requests and reduces the amount of data we need to load from disk. Loading less data into memory enables Amazon Redshift to perform more in memory processing when executing queries. When columns are sorted appropriately, the query processor is able to rapidly filter out a large subset of data blocks. Let's talk about last two features, result caching and compiled code. To reduce query execution time and improve system performance, Amazon Redshift caches the results of certain types of queries in memory on the leader node. When a user submits a query, Amazon Redshift checks the result cache for a valid cached copy of the query result. If a match is found in the result cache, Amazon Redshift uses the cached results and doesn't execute the query. Result caching is transparent to the user. Result caching is enabled by default. So we can disable result caching for the current session. We need to set the enable result cache for session parameter to off. The default option is result caching is enabled. So we can always disable to set this enable result cache for session. Amazon Redshift uses cached results for new query when all of the following are true. The user submitting the query has access privilege to the objects used in the query. The table or views in the query haven't been modified. The query doesn't use a function that must be evaluated each time it's run, such as getDate. The query doesn't reference Amazon Redshift Spectrum external tables. Configuration parameters that might affect query results are unchanged. The query synthetically matches the cached query. So all these, the conditions are true, then Amazon Redshift uses cached results for a new query when all these conditions are true. Let's talk about compiled code. The leader node distributes fully optimized compiled code across all of the nodes of a cluster. Compiling the query eliminates the overhead associated with an interpreter and therefore increases the execution speed, especially for complex queries. The compiled code is cached and shared across sessions on the same cluster. So subsequent executions of the same query will be faster, often even with different parameters. Now let's talk about columnar storage one more time. We discussed a little bit in the features. Now let's talk about this columnar storage in detail. Columnar storage for database tables is an important factor in optimizing analytic query performance because it drastically reduces the overall disk input requirements and reduces the amount of data we need to load from disk. In a typical relational database table, each row contains field values for a single record. In row-wise database storage, data blocks store values sequentially for each consecutive column, making up the entire row. If block size is smaller than the size of a record, storage for an entire record may take more than one block. If block size is larger than the size of a record, storage for an entire record may take less than one block, resulting in an inefficient use of disk space. In OLTP applications, most transactions involve frequently reading and writing all of the values for entire records, typically one record or small number of records at a time. As a result, row-wise storage is optimal for OLTP databases. Using columnar storage, each data block stores values of a single column for multiple rows. As records enter the system, Amazon Redshift transparently converts data to column storage for each of the columns. An added advantage is that since each block holds the same type of data, block data can use a compression scheme selected specifically for the column data type, further reducing disk space and input. The savings in space for storing data on disk also carries over to retrieving and then storing that data in memory. Since many database operations only need to access or operate on one or a small number of columns at a time, we can save memory space by only retrieving blocks for columns we actually need for a query. Where OLTP transactions typically involve most or all of the columns in a row for a small number of records, data warehouse queries commonly read only a few columns for a very large number of rows. Let's talk about workload management. Amazon Redshift workload management enables users to flexibly manage priorities within workloads so that short, fast-running queries won't get stuck in queues behind long-running queries. Amazon Redshift workload management creates query queues at runtime according to service classes, which define the configuration parameters for various types of queues, including internal system queues and user accessible queues. When we run a query, workload management assigns the query to a queue according to the user group or by matching a query group that is listed in the queue configuration with a query group label that user sets at runtime. With manual workload management, Amazon Redshift configures one queue with a concurrency level of 5, which enables up to 5 queries to run concurrently, plus one predefined super user queue with a concurrency level of 1. We can define up to 8 queues. Each queue can be configured with a maximum concurrency level of 50. The maximum total concurrency level for all user-defined queues is 50. Now, how to migrate data to Amazon Redshift. Using Amazon Redshift with other services, we will talk about how we can use Amazon Redshift with other services. Amazon Redshift integrates with other AWS services to enable us to move, transform, and load our data quickly and reliably using data security feature. These are moving data between Amazon Redshift and Amazon S3. Using Amazon, we will discuss about using Amazon Redshift with Amazon DynamoDB, and how to import data from remote host over SSH, and how to automate data loads using AWS data pipeline, and how to migrate data using AWS database migration services, that is AWS DMS. Let's talk about moving data between Amazon Redshift and Amazon S3. Amazon S3 is a web service that stores data in the cloud. It's same like Azure Blob Storage and Azure Data Lake Gen 2. So where we can store massive data in Gen 2, if data is less than 250 GB, then we choose Azure Blob Storage in Microsoft Azure. In the same way, in the Amazon, we can use Amazon S3 to store the data. Amazon S3 is a web service that stores data in the cloud. Amazon Redshift leverages parallel processing to read and load data from multiple data files stored in Amazon S3 buckets. And Azure, we call Azure Blob, when we create a container, we call it container. And Amazon S3, when we create something, we call it as a bucket. And so we can move all the data from on-premise or different sources to Amazon S3, where we can store all kind of data. We can also use parallel processing to export data from our Amazon Redshift data warehouse to multiple data files on Amazon S3. Let's talk about using Amazon Redshift with Amazon DynamoDB. Amazon DynamoDB is a fully managed NoSQL database service. We can use the copy command to load an Amazon Redshift table with data from a single Amazon DynamoDB table. How to import data from remote host over SSH. We can use the copy command in Amazon Redshift to load data from one or more remote hosts, such as Amazon EMR clusters, Amazon EC2 instances, or other computers. Copy connects to the remote host using SSH and executes commands on the remote host to generate data. Amazon Redshift supports multiple simultaneous connections. The copy command reads and loads the output from multiple host sources in parallel. How to automate data loads using AWS data pipeline. We can use AWS data pipeline to automate data movement and transformations into and out of Amazon Redshift. By using the built-in scheduling capabilities of AWS data pipeline, we can schedule and execute recurring jobs without having to write our own complex data transfer or transformation logic. How to migrate data using AWS database migration service, that is AWS DMS. We can migrate data to Amazon Redshift using AWS database migration service. AWS data migration service can migrate our data to and from most widely used commercial and open source databases such as Oracle, PostgreSQL, Microsoft SQL Server, Amazon Redshift, Aurora, DynamoDB, Amazon S3, MariaDB, and MySQL. So far in this module, we discussed about Amazon Redshift Cloud Data Warehouse and what is the system and architecture overview, and we discussed about data warehouse system architecture and performance, columnar storage, workload management, and how to use Amazon Redshift with other services, and how to move the data, how to import out, how to export the data. If you have any questions on this Amazon Redshift, please post in the comments. If you like this video, please subscribe and share the channel. Thank you.